allow me. I'm not sure who else will. Thank you for asking me to speak. Yeah. So I'm going to talk about proving an execution of an algorithm correct, rather than being more ambitious in proving the algorithm correct. And this, I was originally prompted by people at IPAM to give this, and I gave an early version of this talk at Kickham last year, and I think I've got the magic piece of text here for this seminar correct. I cut and pasted. Yeah, okay, so obviously what we'd like to do, we'd like to trust software. We'd like to trust our software. Of course, there's a slight technical problem is that unconditional trust is essentially impossible because of incompleteness. But we've got about one. Of course, theorem provers likely tend to have a small kernel, ideally in the hundreds of lines. I don't think it still is that small anymore, but a small kernel. And all the rest of the theorem prover doesn't actually need to be trusted in the same sense, because if there's an error there, then the proof won't actually be a proof. Obviously, it would be painful if it doesn't work, but it's not actually a blunder in the sense of having incorrect systems. We'd like to make those kernels as small as possible so that we can check them. It's possible to build bigger programs, and the example I know about is Britain's National Air Traffic System, which has hundreds of thousands of lines of code about which you can prove some formal properties. Hey, that's much better, isn't it? Yes. The proof is, however, in this case, the proof is constructed along with the program. It's essentially impossible to prove a sort of 100,000 line program correct if you didn't construct the proof along with it. And indeed, that program is probably incorrect. Almost all 100,000 line programs are incorrect in some way or other. Indeed, there's an example recently. My friend Rod Chapman took 100 tweets, which is what, 1,000 lines? 1,000 lines program. Which have been written by a very good program, have been quite well tested, and he actually verified it, and it failed to verify. There was a 1 in 2 to the 64 bug in it. And that's not bug you just won't find by testing. And so if we can't get 100 tweet programs correct, we probably can't get 100,000 line programs correct unless we build the correctness proof with them.
What the notion of formal proof you use for the UK National Air Traffic System?
It's a proof that it does not crash, a proof that it has no out of bounds rights.
In a system or on paper?
In the system.
Do you know which system they use?
Yes, it's Spark. It's a verified dialect of Ada.
Okay.
And it's a Spark NAT, I think is the name of the Ada theorem prover. Yes.
But you said there was an issue with it? Well, what was the issue and how did it relate to it?
Sorry?
What was the issue with it?
No, I'm saying it is possible.
Oh, it is? Oh, okay. So that one was verified and there wasn't an issue.
Yes. But I'm saying the proof was developed along with the theorem.
So you're saying they have partial correctness and termination?
Verified, termination, yes, termination, and partial correctness, yes.
Well, hopefully it doesn't terminate, actually, because...
Yeah, but and the hard part, which required a lot of interactive theorem proving, was proving some of the geometry constraints that sort of planes don't get within 5 kilometers of each other unless there are at least 1,000 feet difference in altitude and that sort of thing. That's how. So, and that seems to be about the limit of the size of things people are prepared to actually pay for and build. Which, if you come to this thing from computer algebra, as I do, is bad news, because a typical computer algebra program is tens of millions of lines and probably goes back 40 years. If you look at that, the hope of verifying that is really essentially zero. So if plan A doesn't work, what's plan B? And plan B says, can I prove that this particular calculation it did is correct? I'm not saying it's correct all the time. Is this calculation correct? which at least is at least a smaller task. It might be a more manageable task. And I thought when I stood up at IPAM 15 months ago, I thought this was a great idea. And then someone pointed to me a paper going back, 13 years now, which also seemed to have much the same idea. That's some quite good terminology. They said that the certifying algorithm is an algorithm that produces, along with the output, a witness to it. So you get back the output Y and the certificate W, and you check that W proves that Y is the correct output. That was our idea. It doesn't seem to have gone very far. It was their idea, and I'll borrow their terminology to some extent. And that's particularly relevant when Y contains negative assertions. So if you ask it to compute something and it says this is the answer, you can generally check it quite easily. If it says there is no answer, or it says this doesn't happen, that's much harder to check in general. Right, at this point I should warn all those people who've heard me before at IPAM or Kickham and are falling asleep, because now it's time to wake up because this section is new. One of the advantages of being an old professor is that people send you PhD theses that no one else will dare examine, so you end up learning new things. I've been learning new things about convex optimization. So we're optimizing a convex function over a convex domain. And I can write down a function and I can assert it's convex, but you might find it quite hard to prove it's convex. I can write down a domain and I assert it's convex, and you find it quite hard to prove it's convex if I write it down quickly. So it turns out that the optimization people invented this concept of disciplined convex programming. That was their terminology. Essentially, it's a problem that's obviously convex. Under some definition, it doesn't much matter here. And then you get this sort of workflow. You write down a program in what he calls standard form, which basically just says, optimize this thing subject to these conditions. And then you do various, typically manual transformations, put it into the DCP form. And then this group, having defined DCP, then went on to produce a program that converts it from DCP into what's called conic form, which is a very particular form of optimization. It's not just any old convex set, it's just a cone. And you can throw, at this point, we can throw any one of a variety of standard numerical software at it, because the problem is now very well defined in a very simple format. There are many fewer equations involved, and so on. But then, of course, you take the answer from solver, you transform it back, inverse DCP into DCP form, then you've got to undo your manual transformation, get it back into the language you started with. And as I said, that part I've called pre-DCP here is generally done manually, and it's a symbolic transformation. The DCP is, at least at the time, these people, their program is several years later, but there was a symbolic translator, but it was not verified. And point out, there actually are bugs in it. Not that many, but there are bugs in it, and there's a reference there to a GitHub error. The solver is numerical code, it's unverified, and I don't want to get into the business of verifying floating point, thank you very much. For the purpose of this talk, we believe the verifier is being run by enough people that we're actually going to take it on faith. Otherwise we end up in frequent problems. And then, as I say, you invert the DCP, you have to invert the pre-DCP manually. And that was the state of the art until these guys started working, this guy and his colleagues started working on it.
I'm sorry, why do you want to invert this
Because
process?
you want, So, I got my original problem in standard form, and then if I go, by the time I've done all this, my problem is completely different. Well, it's the same problem in one sense, but it's expressed completely differently. We've probably taken logarithms and we've done all sorts of transformations. So it's no good knowing that the solution to the numerical problem is that. I want my solution in terms of the language I posed the original question in.
Right, okay.
Yeah. So it's get back an answer it's an answer that the person who asked the question can understand. It's no good saying, after I did all this transformation, the answer to the transform problem is that. Well, yeah, what's the answer to my problem? Yeah, that's the point, yeah. So yes. And of course, the transformation and the inverse need to be inverses. Yeah. Yeah. And last year, these people produced, Fernandez Mier and his colleagues produced a program called CVX Lean in Lean, which did the DCP transformation and its inverse in Lean. More precisely, given the original problem, it produced a reduced problem in DCP format and produced a function from a solution to the reduced problem to a solution to the original problem. So that's where it's DCP inverse, yes?
I'm pretty sure that they also had some thing for the pre-DCP stage as well, where there was some interactive they would use the interactive.
Yeah, I'll come to that, yes. Yeah. But the actual CVX Lean in automatic mode is a DCP computer, because DCP is sufficiently well specified. That's why it's called disciplined convex programming. You can actually write an algorithmic converter. This is non-trivial. I said the previous one had bugs, had at least one bug in it, but yes. And then also translates the whole thing into floats with some care, but of course there's always problems here. Computes numerical data, writes an external file in the conic format. So it's done, that's the complete forward translation. Calls a particular program, moves it back as a solution to prop.reduced, then the reals, converts it back by using, declares a solution to prop reduced, using sorry, to say, you have to believe that this code did it. And then it uses this reduction from this step to convert it back a solution to prop. So that's DCP and DCP inverse for DCP. And essentially, that's the part we're talking about, and that, as I said, is in Lean and verified. That part we take on faith. And then, since then, particularly in this PhD thesis I'm examining, but it was work by the team, where you start looking at this translation. And this is much harder because so-called standard form, basically it's any form you like to write down an optimization problem in. It's currently not algorithmic, unlike the DCP to conic translation. And it says, there's very few restrictions as long as they are mathematically convex, which doesn't even mean they're constructively convex. I mean, it just means that some mathematician says they're convex. Of course, that mathematician might actually be wrong as well. So several ways of posing a set of tactics that will do these conversion. Can be used to, as you said, interactively or semi-interactively to guide these conversions. And so as well, there's a difference between being convex and being explicitly convex. DCP is in that sense explicitly convex. And the example in his thesis is you minimize x subject to x greater than 1,000th, and whatever root x is less than x to x. And this is not convex because x is an upper bound, and for it to be explicitly convex, the upper bound has to be concave. And it's not. and we can transform it. So this is the transform problem, and in some sense, mathematically but not necessarily algorithmically, that's an obvious transformation and that solves it. Now it is explicitly convex, that is convex, and it is explicitly convex. In the sense that, you can verify x minus x is convex, root x is concave, that's a linear constraint, so therefore it's convex, and hey, I now know Q is convex. I know that. Well, not do I know it, it's blatantly convex. However, this isn't simple as that. Notice that we actually need this little constraint on x to make sure that the 1 over root x is actually valid. If I allowed x to go down to 0, I then have other problems in specification. In general, of course, the other problem is that which is not so much theorem proving as exploratory. We're given P, we have to find the Q, which is explicitly convex. And so there's a set of tactics, and there's a system he has which generates paths through the tactics using equality graphs and so on, which I don't want to go into here. It's interesting, but it's not relevant to the.
So the input is
P.
lean.
Yes.
And then the only goal is to transform it to something convex, or
Something which is explicitly convex. Yes.
well, it can be sort of anything, or do you prioritize among the convex transformations? Are there better ones or worse ones?
Probably ones that cause Mosec not to terminate.
So he has a graph system, and he prioritizes the shortest path to the graph. I haven't finished reading that chapter of the thesis yet. But there's some quite good stuff there on orienting rewrite rules and equality graphs and so on. And there's scope for another talk when I finish reading the thesis about how to do that discovery of Q. But the point I want to make point of view of this talk is that here is a problem where we're not asked, are all transformations correct? We're asking, have I transformed this P into a Q, and B then into a conical thing, and also are the inverse transformations correct? Which is a question we don't often get asked, but it is equally important from the point of view. And of course, just as you have to develop the theorem, the proof with the program, so you also have to develop the inverse transformation with the transformation, and the key theorem is one that says they actually are inverses. That's convex optimization. And I want to go on to talk particularly about cases, a slightly different sort of case where the answer from the computer algebra system or the software was no. And why should we believe that? So of course, SAT solving is this sort of quintessential NP problem. There have been SAT contests and so on for a long time. A mortal point, the definition of SAT, you produce either a satisfying assignment or you produce the assertion unsat, but there is no satisfying assignment. And if you have a satisfying assignment, it's easy to verify, which is why it's non-determinist polynomial time. Testing the satisfying assignment is trivial. The problem is, the first reason, work the second. Ever since 2016, contestants in the SAT contest have been required to produce proofs of unsat if they claim unsat. And these proofs can be enormous. There's a language known as DRAP, which is quite easy to check, not trivial according to Manhoyle, and these proofs can be up to 2 petabytes of stuff, so you wouldn't want to check that by hand, and so on. But so at least in this domain, people have for 8 years now been asking for proofs of that in this very limited domain.
Do you know what kind of set, the size of the instance that generates this size of proof?
No, I don't know.
They're generally reasonably small. Like I would say the input for a proof like this could be, I don't know, 1,000 lines, 10,000 lines, something like that.
10,000 lines of.
Of like the CNF.
Of the CNF, yes. The input to these things is a CNF. We can look at Hoyle's paper, which tells us that, yeah. An algorithm different case was polynomial factorization, which was taken up some time ago. So the challenge of polynomial factorization is you're given some polynomial over the integers, and you write the product, and you claim that these factors themselves are irreducible. So that's, as it were, the hard part. Verifying that it is the product is actually relatively easy. The hard part is verification that there is no more factorization there. I've finished the job. And I don't know of any polynomial factorization program that produces any evidence, never mind a proof. You know, they all just say, I am written by experts, I'm telling you this thing does not factor anymore. Let's look into that. So I want to do, so whereas in this style we could think of it as saying you produce either a factor or you claim that the polynomial has no factors, no non-trivial factors. I'm going to assume polynomial square free simply because that's a separate question and it's a relatively easy one, but otherwise I end up saying square free everywhere and so on.
So are you here in particular claiming that nobody in any proof assistant has done some sort of...
No, I'm saying no computer algebra system
Oh, okay.
that produces anything other than a Boolean assertion. Yeah.
I think it's a good question, though. I mean, are there any are there any factorization tools in existing proof assistants anywhere?
I don't know. I believe there is one in Larry had one in Isabel, I think.
I suppose when you're doing a factorization tool, you could also just implement a thing which returns the FIs and proves the equality to the product, and then doesn't prove irreducibility of what remains.
Yeah, yes. The challenge is proving irreducibility. So, I mean, the computer algebra systems do compute the irreducibility. The point is they don't actually prove it. This is a question I want to go into. Whoops. So the basic algorithm goes back to Zassenhaus, 55 years ago. You choose a prime, you factor f modulo the prime, and they're good algorithms for that. Ignore step m for the time being. Obviously, if it's irreducible modulo p, it's irreducible over the integers, because if it factor over the integers, it would factor modulo p. You now let b be such that any factor of f has coefficients less than b. And Mario was trying very hard to help me yesterday produce a lean proof of that, and it's one of those similarly but isn't as similar as you thought it was proofs, so we're still stuck on that. When you choose an n such that p to n is bigger than 2b, the reason I want 2b is the coefficient between minus b and b, so I've got 2b options. I then use a piece of maths called Hendel's lemma to make my factorization be modulo p to the n, and then I first try each of the FIs and say, do you divide? If you do divide, you're a factor, and you're irreducible because you came from mod p, irreducible factor. If none of them divide, I take pairs of them, multiply them together, and see if that product divides. If it does, it's a factor, and it's irreducible because had it split, I'd already have done that. So I did the singletons first. Then I do the pairs, then I do the triples, and so they are indeed irreducible. You can use other techniques as well if you want. And in practice, there are an awful lot of optimizations which complicated proof of correctness of the algorithm I've just given, and we actually did an implementation. I wasn't actually writing it myself, but I was in the same lab as Mary-Ann Moore and Arthur Norman, and that's their comment that it was about the nastiest piece of code we've ever seen by the time they put in all the optimizations and so on. Now, if R is reduced from mod P, it's reduced by the integers. If you find the factors from singletons, they're easily proved irreducible because they're reducible mod P. You did that. The trouble is that the chance of polynomial mod n being irreducible mod P is only 1 over n, so this doesn't happen very often. Not with real size polynomials, not with sort of realistic size polynomials. You could relatively easily produce the information that you needed for a proof, unless you needed a combination. You'd say, I chose the prime 7, here is my factorization mod 7, and there are easy ways of checking factorization mod P, and hey, this is the factor that corresponds. Oh yes, so it is. You don't need to verify the Handel's lemma, you don't need to prove that's correct, you just say, hey, yes, it does divide. And that does it. So we just have to verify the Handel's lifting, not actually compute it. You prove that they've got the right degrees for factorization mod P, and not give F modulo P to the end, therefore are the right factorization. That's great, because the real problem Mary-Ann Moore had was building all the test cases for all the edge cases and so on, and actually trying to find a polynomial such that I could check whether I got 2b rather than b, so I need a polynomial of factors as factors very close to the edge and so on and so forth. We only do that in the proving stage. Great. The Handel's lifting stage is easy to verify. It divides, and we've checked all the previous combinations. If you don't use it, if you use one of the variations, it's much harder, but that's a separate problem. Okay, but I don't know an easy proof if your alternative says irreducible. I can only currently work with step H, not its variance. That's okay, that's okay. So the other proof is, it says you take 5 primes and compare the factorizations. You don't just take the best, you actually say, wait a minute, I want any factorization of integers must be compatible with all of these bits of information put together, so you've got a bit of a jigsaw puzzle. So for example, if a degree 4 polynomial factors as 3 times a 1, and it factors as 2 times a 2, it's actually irreducible because there's no factorization which is compatible with both of them. That's a great advantage of step M. So one open question which I'm still very thinking about is, what is the best division of labour between the algebra system and the theorem prover here? And that's a good question, which probably depends on both the algebra system and the theorem prover, I suspect. It says 5 times, there's recently research that says 7 is asymptotically right. If assuming the Galois group is Sn, the probability if the Galois group is Sn, it tends to 1, so that's the right thing to look at. Provided doesn't actually go wrong in other cases, which it doesn't do, that's okay. Those work on other group, yeah. Okay, so that's factorization. So the hard part is saying irreducible, and as I say, no one actually does that. Mario?
When you said take 5p, which 5?
You normally take the first 5 such that it stays square free.
So,
But 2, 3, 5, 7. You don't take 2 because 2 is a very odd prime. Yes. 3, 5, 7, 11, 13, provided it stays square free. Yeah.
so if one of them, so there's like some notion of like this prime is special, let's give it the next one.
Yeah. So the algebra will emit which primes it actually used. Yeah. and we're asked to switch them. But the cost of doing factorisation mod P is polynomial in log P, so you want a small p.
Also, something about like the way you showed this like algorithm, I'm wondering why you don't say like at the beginning, without loss of generality, assume that f is irreducible. And then a lot of this just simplifies, right? Because for the certification task, that's the only case we care about. We don't care about the non-divisible, the case where it has factors and then those factors are irreducible, because that's just multiple cases of irreducibility proofs, right?
Yeah, but then what you have to do is you have to ask the algebra system to go back and recompute its evidence for that.
Well, I mean, you're going to be replaying this argument, half in the theorem prover and half in the computer algebra system. Whatever mechanism you're doing there is probably going to look something different from the original CAS algorithm. So it seems easier just to start from there.
Yes, and indeed, for the first proof of concept, that's what I'm going to do. I'm not sure you want to do that in production, because you'd have to, if it factored into two polynomials, you want the proof of those two are reducible, rather than to say, oops, okay, now let's go back and factor each of those to prove they're reducible.
I mean, does this mechanism give you an easy way of proving the factorization of those pieces? I mean, it doesn't seem much easier, right? You can still just rerun it over unless these are like really big polynomials or something like. Who cares if you run it twice?
From the point of view of runtime, it's only going to be a constant factor anyway. Probably only two or something. Yeah, you could. My scenario initially was that it would be, the cost of producing the proof would be negligible overhead, so it would always produce the heads. What you're suggesting is is not that, but equally it's not expensive. It depends.
Well, I mean, you can take this algorithm and then you apply it for an f which you believe to be irreducible.
Yeah.
And we're not really interested in the cases when it's not. And then you just consider what would this algorithm do, and like there's a couple places where it says, oh, irreducible. Like one of them is the integer factors don't match up. Another one is this h prime says irreducible. And then I guess dig into why does it say that, it's got some theory behind what it thinks that is the justification of irreducibility.
Yes, I could. Yes, I mean, one could. I mean, I came from pure algebra. I wanted to minimise the extra burden on the algebra system. I said, let's just write out a trace of what I've done and let the theorem prover work out what that means. But yeah, an alternative is, as you say, to only ask about irreducible polynomials where I've got all the evidence. Yeah, you're right. That is an alternative, yeah. Another area of pure algebra which is used a lot, and in fact where I cut my teeth, is integration. Let's imagine a professor and an awkward student. The professor says e to minus x squared has no integral. And the awkward student says in analysis, the professor proves every continuous function has an integral. The professor says, well, that means there's no formula for the integral. The student says, but in statistics, the professor used for x and everything seemed okay. Well, that was no elementary formula in terms of exponentials, logarithms, and the solutions of polynomials. How do you prove that? And the answer is you use differential algebra, which is good news because it's algebra. In some sense, theorem provers tend to be better with algebra than they are analysis or topology. And differential algebra is essentially you just take a field and you equip it with a differential operator such that the derivative of the sum of some derivatives, and you've got the product rule. And in fact, if you've got the product rule, the quotient rule is in fact a corollary. I wish I'd known that at school rather than having to prove it by hand. In fact, yeah. And there's an algebraic theory of integration, which is in Joseph Ritt's book as a formalization of what actually Joseph Liouville knew. So you take some function where x dashed is 1, that's what makes x the variable of integration. If thing's derivative is 1, that's what I'm integrating with respect to. And each theta I is elementary over the previous one, over the field of all the previous ones. So I've got x, then log x, then log log x, then log 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 x, and so on. Or I've got x, an exponential of x, an exponential of exponential, or exponential of 1 plus log x, or all sorts of things. You actually need to ensure the field's decidable because of various undecidability problems. And then what you do is you want to produce either some capital F in some elementary extension of L, such that the derivative of this capital F is the original, in which case you found your elementary integral, or you want to prove there's no such elementary integral. Now the first one you can verify. If I say here's a capital F, you can at least in principle verify. What about the second one? Actually, of course, the verification isn't trivial. There are all sorts of issues about simplification of elementary functions. Because of branch cuts, capital F might not denote a continuous function. The student's memory of analysis will tell the student that any integral is continuous, but it doesn't mean that any formula for an integral is continuous. Because the Heaviside function differentiates to 0, so in terms of differential algebra it's a constant because the derivative is 0, and you get step functions coming from branch cuts of arctan and so on. Let's ignore all those problems for the time being. They're great fun to prove, but that's a separate problem.
Does that mean that you have to, does this mean that you can ignore the Heaviside functions, or that you will have them everywhere and they don't count in some
Well,
sense?
yeah, if you get them in the output, then if capital F starts containing them, then you have to work rather harder to prove that capital F is actually a formula of a continuous function. So if you differentiate capital F and you get a small f, that's great. But since integrals have to be continuous, capital F has to be a continuous function, and where it's written down with arctangents might have branch cuts in it. So you then need to prove that those branch cuts are superly compensated by adding Heaviside functions to cancel the branch cuts. That's a completely separate issue, which Corliss and I did some work on, and not been done in theorem provers yet. That's a good challenge for someone. Hey, prove this integral actually is a continuous formula. Good question. If you say looking for any elementary integral at all, what about looking for a needle in a haystack? Hey, I can think of lots of formulae. Well, there's a theorem due to Liouville, which says that if there's an elementary integral, then that elementary integral has to be something in the original field. The VI's are in some algebraic extension by constants, only by constants. And the CI's are constants. So all I get is algebraic numbers here, algebraic constants here, multiplying new logarithms of things. That's all I get. So I'm not actually looking for neither in a haystack. I've actually only got a single bale of hay to look in. Another way of looking at it says you can express little f that way. Because then if I integrate that, I get that. And the proof is by equating coefficients. So the algorithm is due to Bob Risch. It says that and here I'm going to assume the theta I are either algebraic or logarithms. I'm going to ignore the case where it's algebraic. And I do it by induction on n. It's a two-legged induction. I induct that I can either solve or prove insoluble integrals, which have to be of that form by the Liouville theorem previously. But also, I need to solve or prove insoluble that I can solve y dash plus fy equals g for some y in the same field but without new constants. And it turns out that if you set up your induction hypothesis that way, it works. And the algorithm is a very messy comparison of terms argument. You say, well, what can my integral look like? What's the highest degree on both sides? Compare the coefficients recursively and repeat. Indeed, there was a classic case of a similarly here, which actually wasn't quite had to write a paper fixing up the similarly. The mess comes in showing that this is complete and that this sort of bug fix is complete as well, and so on. Each individual case is quite straightforward. So to produce, how we produce a proof of bottom bend? Well, A, you need the formal proof of the Liouville theorem. I haven't done that, but it is actually all algebra, differential algebra. And then at each point where the algorithm is comparing terms, it needs to split out a proof that it's compared terms correctly. But I had an implementation in Axiom which produced a very stylized informal proof. So I'm fairly sure this is doable. But I'm not considering the algebraic case, I said. That was in my PhD thesis, and the trouble is there's much more mathematics involved, which I think, let's see, and more general theta I is treated in Bronstein's work, and again there's more mathematics. So if you want to do mathematics, if you want to do the algebraic case, you may end up asking questions like, is a divisor on an elliptic curve a torsion divisor? You end up going back to, in that particular special case, you end up using Mazur's theorem. And Anne Barland says she thinks it might be formalizable. But yeah, we're asking now for PhDs in formal proof theory.
Is this the same Master's theorem that's going to come up in FLT?
Yes. So maybe done for me, yes. I don't think it's been done yet, I don't think. Yeah. Okay, so the next problem, the last one I want to do is real quantifier elimination. Tarski and Seidenberg said, so if I've got QIs either exists or for all, and I've got a bunch of quantified statement, so I have an exists with possibly several variables, and then a for all with several and so on. We've got A plus 1 quantifiers here with lots of variables, and a statement here, which is a Boolean combination of equalities and inequalities between real polynomials. It's over the reals. Then produce another Boolean combination of equalities and inequalities in the y's only. So the y's are the free variables here, which is equisatisfiable. And that's a compilation problem. And it's not all obvious it's even possible. And indeed, that's the Tarski-Seidenberg theorem. And we say that and it can in fact be done so that the coefficients are integers, and then we have Tarski formulae. The proof decided in the 50s. The first feasible solution was by George Collins 49 years ago. And as I said earlier about long-lived software, there's a program, WebTasky, you can do it on the web. It actually relies on George Collins' 1970s Fortran, which got translated into C in the late 1980s, and has now been mapped into WebAssembly. And there's quite a lot of it as well. Yeah, in fact, it works at all. It's quite remarkable. Yep. So what we do is we fix coordinates consistent with the order of quantifiers, and you then produce a set of cells which are cylindrical in the sense that for all I, j and k, if I project ci, oops, that's really cj, sorry, j, sorry. I project ci and cj, I either get the same projection, so they're on top of each other, or I get disjoint projections. They can't overlap. Elsewhere, I could find my polynomials, and their decomposition, so they're disjoint, they cover Rn. And also, it does the same as each cell has a sample point in it, which in particular means the cell is non-empty, which is quite useful. And then you do it, and on each cell, every polynomial is sign invariant. Then the truth of phi is invariant on each cell, and you write down psi as the truth of those cells on which the projection is true. And you only check the sample point because it's invariant across the whole cell. It's W exponential in n, so CAD's worst case is W exponential, and in practice it nearly always is in the number of variables. So CAD doesn't care about quantifiers, which means that the SAT problem is their solution, or is in fact my formula void. Isn't a special case, it should be. It doesn't care about the Boolean structure, and we can do better. There's various work by Scott McCallum. We can even the only equality somewhere. I'll skip over that one, that's algebra, really. And the more you improve it, the more maths you need to import. You need the multidimensional Puiseux theorem and so on, which we probably, I wouldn't like to formalise. And the group around Georges Gontier tried to formalise the basic Collins algorithm and failed. When Georges Gontier's group fails, I'm not going to try. So a different algorithm comes out of. So Eric Abraham is a professor in Aachen. Which looks purely at existential problems. And for the sake of simplicity, I'm going to assume we just have greater thans and less thans. You can do it with the other forms as well. And I write my formula in normal form. I then commute exists and ors and treat each or separately, which means that unlike Collins, I don't care where P11 and P21 intersect because they're in different branches. It doesn't actually change the asymptotics, but in practice it's damn useful. You choose a sample point at random. If it satisfies the formula, we found a witness. If it doesn't satisfy the formula, then one of these things is false. And I remember it. I compute the largest interval in which it's still false. If it's not the whole real line, I choose some other sample point, some other SN, a new SN, keep all the old ones, but have a new SN, not in that interval. Again, if it's true, it's a witness. Otherwise, I keep on repeating this until I cover the whole of R for that S1 to Sn minus 1. I've now covered the one stalk. And I might want to do some pruning here. Each of those ones defines an oval in Sn to Sn minus 2 xy space, in which and they cover that space. I compute the largest interval such that for all xn minus 1s, they cover that space. So they covered it for Sn minus 1. By now enlarge Sn minus 1 as much as I can. If that's not the whole R value, I choose a different value of Sn minus 1 outside this interval and repeat until I cover the whole of Sn minus 2R. And I keep repeating again. Termination isn't entirely obvious, but in fact, The CAD is finite. Every cell I produce is at least as big as the CAD cell, so that's finite. And the point is, all I'm doing is simple algebra, are they in, are they not in? And the question is that verifiable? Very much work in progress. And one of the things I want to do here is at least think about that. There are at least two distinct options. You can verify each non-redundant, so actually prune it. After you've done it, you prune it. You discover I created this small interval, but I shouldn't have bothered because actually there's a bigger interval elsewhere. Well, in the same place that does it. Elsewhere in the proof tree, but in the same place in our N that covers it. So I'll do some pruning. And you take each interval in R1 and it's covered because each interval in R2 but covers that cylinder and that's covered because and so on. You essentially reverse engineer the proof. And you have to remember all the polynomials you used. Or could perhaps produce a rough CAD and reverse engineer that. For each sample point, you check that the appropriate cuboid is contained within the polynomial does not satisfy the right relationship. You verify these cuboids are cylindrical and complete. But to do this, I need lots of results and inequalities, but no topology because my whole thing is cylindrical and I'm putting together cuboids. Or if you like, I am doing topology, I'm doing total trivial topology. And I'm not sure which is the best. That's one of the things I want to think about here. And so my conclusion is that UNSAT is much actually often more difficult than positive answers. Completeness proofs of algorithms can be challenging, yes. And that we don't need the completeness proof if we've got the proof of it for this example. So, but we do need, as it were, as I said in the case of factorization, to keep the hints. Possibly can't do it in all circumstances. So we ask, is this still valuable? I don't know, that depends on the user. And there's a whole bunch of references. I'll email my slides, whoever I need to email them to, and those references will chase up various problems, and I'm eating into coffee time. Thank you.